Okay, so in this video we will discuss a little bit about relative velocity and acceleration expressions in a rotating frame. Now the relative velocity and both the relative velocity and acceleration expressions in rotating frame are very frequently used in solving rigid body problems. We will try to provide a physical intuition of what the relative velocity or how the relative velocity manifests in a rotating frame, and then from there we will derive this relative acceleration expressions in a rotating frame. We will try to give an intuitive understanding through an example, so that at least the relative velocity expression that we have is not just a mathematical expression, but you will see that the individual terms in that expression has a pretty physically relevant meaning. So we'll try to articulate that through the example. So what we mean by relative velocity in a rotating frame is something like this, where just to give an example, assume that a vehicle is moving in a curved path. Okay, so this is the path that is being followed by, let's say, the geometric center of a vehicle. So at a particular instant, the vehicle is like this, and that's the geometric center. And let's say that, so then the geometric center has a velocity like that. Okay, and let's say that point is Q. Right? Now let's say that relative to this geometric center there is a point P, which could be inside the rigid body, but it could also be extended beyond the rigid body. But let's say that the point P is here. Okay, and let's say, for the sake of convenience, that the point P is the line QP is making some angle alpha with respect to the direction in which the vehicle is moving. I mean, this you could consider similar to, for instance, you are driving a car, and right on the dashboard, a little bit to your right, there is a knob, okay, that you can turn to increase the volume of the audio. So let's say that knob is located at the point P, and it is kind of at 30 degrees from the from your direction in which you're looking outside the car. So the straight direction along the road, from there 30 degrees is where the knob at P is, and it is at a certain distance from you. So this is kind of the scenario. Now let's say that the vehicle you're driving is taking a turn, and you are taking a turn with a velocity v. All right. So an instant or a few instants later, the vehicle is going to be somewhere along here, and let's say that you are taking the turn with a constant velocity. So let's say that's v, and this is the point Q. Then the point P is still making an angle alpha. Okay, and then after a few more seconds, or a couple more seconds, the vehicle is here, and the velocity of the point Q is of course still tangent to the path, and the point P is still making an angle alpha with that path. Now this solid line that we have drawn is the path that is being traced by the point Q, and if we take the path taken by the point P and if we join them by a dashed line, then we see that the path looks like this. All right. So you see that one thing that is happening if you just focus on this line Q to P. This line, its orientation is changing, right? Because as the vehicle changes its orientation, the orientation of P with respect to Q is changing, right? Here the orientation was, let's say, alpha plus some degrees from the vertical. Now here it is much more inclined from the vertical, and here it is further more inclined from the vertical. So one thing that you can see is clearly P is rotating with respect to Q. Okay, and now let's say this Q to P that we consider is a vector rho. So this Q to P is a vector, and we call that the vector rho. So the rate at which P is turning with respect to Q, because clearly you can see that the orientation of QP is changing. It is rotating. So with respect to Q, P is turning, right? And so that rate at which P is turning with respect to Q is omega cross rho. All right. And so if we start by saying that so now let's start from very basics and say that this is some fixed coordinate frame, and let's say that this vector going from the origin of that coordinate frame to Q is RQ, and the vector going from the origin to the point P is RP, right? So clearly we have RP is equal to RQ plus rho. So this is, you can see that rho is therefore the relative position of P with respect to Q, and P is being expressed as a function of RQ and then the relative velocity. So this is the relative position equation. Okay, which relates the position of P and Q in the absolute positions of P and Q through this relative position. Now if we take the time derivative of this, we will have Vp is equal to Vq plus rho dot. Now in this case, so I'm just going to put some notes here. Assume Q rigid, or rather I should say P rigidly attached to Q. So in other words, if you take that example of that knob, the volume knob on your dashboard, imagine that so with respect to where you are sitting, that knob is not only at a constant distance, it's with respect to you, it is almost rigidly attached. Okay, the only case for the instance of the knob where it will not be rigidly attached is if you consider the scenario where you are turning the knob while you are taking the turn, right? So now let us not assume that. Let us assume that the knob is static. So under this condition, you can say that P is rigidly attached to Q, Q being the place where you are sitting on the car. So you are attached to the car. With respect to you, the point P, or the knob, is rigidly placed. So if that's the case, then what happens is that this rho dot becomes VQ plus omega cross rho. So this omega cross rho is capturing the fact that as the relative vector, the relative position vector, as the reference point turns, okay, or as the reference turns, okay, so the reference here is the reference of the vehicle. In this reference you have this vector rho. Now the reference itself is turning, and because of that turn, what happens is that it causes a turn, and in the absolute sense of the vector rho. Okay, so the rho vector is turning by virtue of the fact that the reference frame itself is rotating. So this is due to the rotation of reference frame in which rho is measured, right? So this rho is being measured within the car's reference. So the knob is at a certain distance from me, from the driver, and it is at a certain angle. So that vector changes. That vector is now turning because the car itself is turning. So your reference frame is turning, so that vector is also turning, and because of that there is an additional velocity that is being generated, and that velocity gets added onto VQ to give you the velocity of VP. Okay, and just to see that, so of course this is the case. So you can see here that rho dot is equal to omega cross rho, and we will note over here that this is true when P is rigidly attached to Q. Okay, so when P is rigidly attached to Q, so this should be when P is attached, rigidly attached to Q, then you have this as your rho dot. Now to illustrate the fact that this term, this rho dot equals omega cross rho, this term indeed comes into play when the reference frame is rotating. In other words, if the reference frame was not rotating, then this term would not have come into play. Okay, and so to illustrate that, let us consider an alternate case where the vehicle is now going along a straight line. Okay, so if the vehicle is going along a straight line, so then this is the velocity v, and the point P is here, Q is here, and making an angle alpha. After some time, here is the position of Q. It is still moving with the velocity v, and this is the position of P. And if you consider the locus of P, it is completely parallel to this line. Not only parallel to this line, but its velocity, the velocity with which P would move, is the same as the velocity of Q. Okay, so in other words, when you are driving on a straight street or straight road, then the velocity of that knob on the volume control is the same as your velocity. Okay, so and so here what happens is, so here omega is equal to 0, therefore Vp is equal to Vq, right? So when there is no angular velocity, we see that the motion becomes quite trivial, in the sense that the velocity of the 2 points are exactly equal. The difference in the velocities happen when the vehicle is taking a turn, because when the vehicle is taking a turn, the vector, the relative position from Q to P, that actually rotates, right? Because the vehicle is taking a turn, and because of that, there is this extra term that is introduced, and when omega cross rho, and when added to the velocity of Q, that gives you the net velocity of the point P. Okay. Now let us add another level of, or another motion to this, and that is what we'll do is, now we will say that this point P is now, let's say it's at an angle alpha, but it's rattling about that point. Okay, or in other words, if I take the example of that volume knob, as you are taking a turn, that volume knob is being turned by you. Okay, so if you consider a point on the top circumference of the knob, now it has got a motion. Okay, and so what if that happens? How do I quantify the velocity of the point P in that case? So let's look into that. So now we considered the case where the vehicle is taking a turn, so this is the velocity, this is the point P making an angle alpha, but here at this point, now there is, this point P is rattling, and let's say that there is some motion of the point P here, right? And so what would happen is, a little or a couple of instants later, when the vehicle is here, its velocity is still tangential, the point Q is still here, and the point P has infinitesimally small, so this is, let's say, an infinitesimal instant later, there has been a movement from P to P prime. Okay, so in other words, there is a rattle in the motion in the point P, and that gives an extra velocity to the point P, and so this is almost like that knob that we are talking about. So you are turning the knob as you are taking a turn, and so there is an extra motion that you have given. You can also think of this as a water bottle that you have that is kept beside you as you are driving, and the water bottle is rattling and you are taking a turn. Okay, so there is an extra velocity that the top of the water bottle has, and you are now trying to find out the velocity of the top of the water bottle, okay, based on the fact that you are taking a turn, and the water bottle is at a certain distance from the seat at a particular direction. So let's say the water bottle is now at 30 degrees, so it's there at 30 degrees, okay, but it's rattling as you are taking a turn. So that's the scenario that is being considered here. So one thing that you can see is that if there was no rattle, then this would be the trajectory, but if there is a rattle, then the trajectory would start to get modified, doesn't it? It'll start to get modified because of this rattling. Okay. So this is an extra motion that is now superimposed, and so you still have R P is equal to RQ plus rho, right? So this is the rho vector, and now when we take the derivative, we have Vp is equal to Vq plus rho dot. Now this rho dot, of course there is this angular velocity omega, because that's when these relative velocity terms become more interesting. So you still have the omega cross rho term because that scenario is still happening, but on top of that you now have the rattling of the bottle or the turning of the knob, and so that is given by the velocity in the rotating frame. So imagine that you are now driving in the car, you are watching, you have the bottle, and so you are driving you are taking a turn, and you know that the bottle is rattling, and so let's say you had some sensor that could measure the rate at which the bottle is rattling, and it could give you some velocity data. Now that data, okay, if you are just measuring it based on your visual the fact that you can look at the bottle, you will see the rattle of the bottle, you'll have some estimate of the velocity, let's say, but that velocity measurement or that velocity estimate is with respect to you in the car which is rotating. So it is a velocity that you are perceiving within the rotating frame. Okay, and so that velocity is rho dot r. This is the velocity of that motion of P within the rotating frame. Okay, if you are turning the knob, it is going to be, and let's say you are turning the knob with a constant angular velocity, then the constant angular velocity times the radius of the knob, okay, is the velocity on the circumference of the knob, but that velocity is a velocity with respect to you within the rotating frame. Okay, so that's a velocity within the rotating frame, and that's now an extra term that is being added. So here one thing that we can see, that rho dot r is added when P and Q are not rigidly attached. So they are not part of one rigid body. P is moving with respect to Q. Okay, it is not only at a distance of Q, but it is moving. It is within the rotating frame. It is moving. Okay, so basically is added when this is a thing, and furthermore this rho dot r is due to P moving within the rotating reference frame. Okay, and so we see here that rho dot, keep in mind that when we moved from here to here, then what we did is we took the rho dot. So essentially this term, these two terms, is nothing but rho dot. So rho dot is equal to omega cross rho plus rho dot r. Okay, so anytime there is this relative motion that is happening, within the rotating frame, then this term gets added. You can look at this vehicle turn scenario and show this relative motion within a rotating frame by taking another similar example. So let's say that now we consider the scenario where this is Q, this has this velocity V, the point P is here, making an angle alpha, this is Q, this is the vector rho, you still have the angular velocity omega, and let's say that you are considering a case where the point P is being extended, right? So a couple of instants later, when the vehicle is here, its velocity is still v, this is the point Q, this is the point P, but the point P has now gone to P prime, it has extended a little bit, okay? And so this kind of motion is also very similar to that, in the sense that within the reference frame you are extending it, and often when you make the measurements within the rotating frame, it is easy to quantify this extension. So for example, so just consider the case, for example, where let's say you have a telescopic beam, and that beam is being extended, okay, and the vehicle is taking a turn. So that motion, the rate at which that extension is happening, is relative to the motion of the car. So it is within the rotating frame of the car, okay? And so here also you will have a similar scenario where the point P would have otherwise taken this trajectory, but because of this it is taking a trajectory like this, okay? So here also the same thing applies, and you have rho dot equals this, and so here you would have Vp is equal to Vq plus rho dot, and this is V cube plus omega cross rho plus rho dot r. Okay, so here, as we mentioned, this is where the rigidity is relaxed. So you're allowing the point P to move with respect to Q within the rotating frame. So that's an explanation of how this three-term velocity comes into play when you are expressing the velocity of one point with respect to another, where the relative position between the 2 points is a vector, and that vector is inside a rotating reference frame. So in this case, as you can see, and in this case as well, this vector rho, which is the relative position of P with respect to Q, is a vector that is turning, okay, because of the fact that the reference frame itself is turning, and on top of that it has some extra motion. So those two have to be incorporated, and that's where we get this three-term velocity expression. Now, one question that comes up is can we go from here to derive the acceleration of a particle if this is the scenario, that is we want to express the acceleration of P with respect to Q, and assume that the relative position of P with respect to Q is in a rotating frame. So can we go one step further? And the answer is yes, we can go one step further and come up with an acceleration expression. So let's do that derivation. Okay, so actually let me go to a different page, and I'll start off with Vp is equal to Vq plus omega cross rho plus rho dot r. And we have to keep in mind that this expression is rho dot. This is the net velocity of the relative vector, the relative position of p with respect to q. So therefore AP can be found by just taking the derivative of this equation. So if I take the derivative of Vq, I will have AQ plus, now let's take the derivative of the second term. It's going to be omega dot cross rho plus omega cross rho dot plus we have the derivative of rho dot r. Okay, now we'll deal with this a little bit later. First, let us address this term. There is nothing to be done with this term because this relates to the angular acceleration. So if the vehicle, as in the example that we gave, it is not only taking a turn, but it is taking a turn with an angular velocity that is changing, then the angular acceleration comes into play, and it is going to be relevant when you write the acceleration term of p with respect to q. So acceleration of q plus omega dot cross rho, this kind of term is kind of the tangential acceleration kind of a term, plus omega cross rho dot. Now keep in mind that rho dot has already been used in the velocity equation, and so we can say that rho dot is omega cross rho, and let me put it in parentheses, plus rho dot r, and the last term is d dt of rho dot r. Okay, now going one step further, it's AQ plus omega dot cross rho plus omega cross rho plus omega cross rho dot r plus d dt of rho dot r. Okay, now let us consider this acceleration term. So now consider this d dt of rho dot r. This is the acceleration of that relative velocity within the rotating frame. So in other words, it is the time derivative of that rattling velocity that we were mentioning of the bottle, or the time derivative of the angular velocity that is being used to turn the knob. So how do we find it out? First of all, note that this velocity, the rho dot r term, is a velocity within a rotating frame. It is inside a rotating frame. Okay, so when we take the time derivative, but the time derivative does not care about whether it is inside the rotating frame. It asks the question, what is the net rate at which this vector is changing? Okay, so here we have to be careful. We cannot say that it is simply rho double dot r. We cannot say that, because that would be the acceleration or the time derivative or the acceleration within the rotating frame. Okay, just like rho dot r is the velocity within the rotating frame, rho double dot r is the acceleration within the rotating frame. But that is not what this ddt is asking us to do. What this ddt, which appears when we take the time derivative of this, is asking us to do is to take the entire time derivative. Okay, when you take the time derivative of a vector, you don't care about whether the time derivative is inside or outside. When we say that I want to find a d dt of a certain vector, you are talking about the time derivative of that vector in the absolute sense. All right. But this is not that time derivative in absolute sense. This is the time derivative of that velocity within the rotating frame, okay, but it's the time derivative within that rotating frame. So this is the acceleration within that rotating frame, okay. So what is the net acceleration? The net acceleration is found by observing that this velocity is a velocity that is within the rotating frame. So by virtue of the fact that this is a vector within a rotating frame, we need to also consider the fact that this vector itself is turning with an angular velocity omega. So that is the contribution, because of the fact that this velocity is a velocity within the rotating frame, and well, the frame is rotating. So therefore, by virtue of the fact that the frame is rotating, then this velocity has an acceleration, and that is given by omega cross rho, okay. And so there are these two terms that give the net rate of change of the relative velocity within the rotating frame. So this now gets plugged in, and note that this term is same as this term, and so when we add things up, we need to make sure that we have taken care of the fact that there is a second omega cross rho dot r that is now added. So AP then is equal to AQ plus omega dot cross rho plus omega cross cross omega cross rho plus 2 omega cross rho dot r plus rho double dot r. Okay, so this is the 5-term acceleration expression that relates the acceleration of a point with respect to another point, where the relative position between the 2 points, that is rho, lies within a rotating frame of reference. So what is this expression again? This expression is an expression that relates the acceleration of a point P to the acceleration of point Q, where the vector from Q to P, so keep in mind that rho is a vector going from Q to P. The vector from Q to P is inside a rotating frame, okay, and so if that vector is within a rotating frame, then the acceleration is of the 2 points are related by this expression. Again, keep in mind that if P and Q are rigidly attached, then rho dot r is equal to 0, and in the acceleration expression, rho double dot r is also equal to 0. So if P and Q are rigidly attached, then in the rotating frame there is no perception of P having any motion or any velocity or any acceleration with respect to Q, and so both these two terms, rho dot r and rho double dot r, are 0, and then what happens is this acceleration expression simplifies, because then this term and this term drop off. Okay, now going back to this original expression, acceleration expression, we note that this term is often referred to as a Coriolis acceleration. This term is often referred to as centripetal acceleration, and usually this term gives rise to a tangential acceleration. So that is what I have in this video. we are going to look at a number of examples going forward where we'll be using this relative acceleration expression or acceleration in a rotating frame expression. This is very useful in solving problems of rigid bodies, and we'll demonstrate the use of this equation in upcoming problems. So that is what I have in this video. Thank you very much.